Geneva, and I will be chairing this afternoon's first session on the local dwarf galaxies. So just to remember, we have talks which last 15 minutes, but this is supposed to include roughly 5 minutes for questions. So I encourage all the speakers to stick to this as far as possible, because the interactions and questions are really an important, interesting aspect of this conference. Otherwise, for the talks, during the talks, please switch off your video so that we save bandwidth. And then after the talks or during the talks, actually, you can already ask questions. You can ask written questions on the Slack channel in a thread which is reserved for every talk. And then you can raise the hand if you want to ask questions. And I think with this being said, I think we can start now the session. It's 2 o'clock. And good morning and good afternoon and good evening, everyone, and welcome. And the first speaker is Yumi Choi from Space Telescope Science Institute, who will talk about measurements of escape fractions in dwarf galaxies. The floor is yours.
Thank you. Hi, my name is Yumi Choi. I'm a postdoc at Space Telescope. I'm happy that I finally have an opportunity to talk about my recent results published last year, and some of the preliminary results of our ongoing HST program. Oops, doesn't proceed. Okay, so there is a consensus that the cosmic reionization was driven by abundant small star-forming galaxies. As shown in the UV luminosity function in the left panel, the fainter galaxies are numerous than the brighter ones at any redshift. And on the right panel, I'm showing the cumulative ionizing emissivity as a function of UV luminosity. And you can see the fainter galaxies dominate the ionizing emissivity. However, the details of contribution of UV faint galaxies to cosmic reionization is still unclear. For example, the contribution of UV faint galaxies to ionizing emissivity highly depends on various assumptions. For example, the escape fractions, the ionizing photon prediction efficiency, and faint and the slope of the UV luminosity function, and the faint and limiting magnitude of the UV luminosity function. So typically, the fiducial limiting magnitude adopted in the reionization models are MUV of -13 or -10, but unfortunately, there are no observational constraints on the escape fraction for these extreme UV faint galaxies. And most of the reliable escape fraction measurements have been made for galaxies brighter than MUV minus 19. So constraining the escape fraction for the UV faint galaxies down to fiducial limiting magnitude, -13, -10, are crucial to understand the role of the UV faint galaxies in cosmic reionization. However, in reality, it's very challenging and expensive to make reliable observations of galaxies fainter than MUV of -16 at the epoch of reionization, even with the JWST. So this shows the JWST without the lensing. We probably reached to MUV of -16 at redshift of 7. And furthermore, it's impossible to directly detect the leaking ionizing photons from the galaxies at the epoch of reionization anyway. So looking at local analog of high redshift star-forming UV faint star-forming galaxies is the only way to study the Lyman continuum escape process in this UV faint regime. And although the star formation conditions in the early universe are known to be different than the present day, looking at the metal-poor local dwarf is the only available way to study star formation and the interaction of massive stars with the surrounding ISM in detail at very low metallicity environments. And they may mimic the conditions of early universe at the best. The ionizing photon escape fraction process itself highly depends on small-scale structures because escape fraction is determined by the spatial distribution of the ISM and the massive stars within a galaxy. So, so we really need a small-scale resolution to properly understand the ionizing photon escape process and at the low metallicity environment. And then in the nearby galaxies, it's only possible to connect these small scale processes with the global scale properties as well. And also by looking at the local dwarf galaxies, we can avoid any complexities due to the lower redshift interlopers or uncertain IGM transmissions. And once we obtain the detailed knowledges about the Lyman continuum escape processes from the local universe, then we can apply that knowledge to interpret the observations of distant galaxies. By definition, by my definition, the local, I mean the local volume, more specifically within like 4 megaparsec, where the HST can resolve a galaxy into individual stars. So at redshift of 0, it's impossible to directly measure the Lyman, the leaking Lyman continuums because there is no instrument detect any emissions below the Lyman limit. Even exist, all the escaping Lyman continuums will be likely observed by the Milky Way neutral gas before reaching us. So we come up with a new indirect methodology to measure the escape fractions in the nearby galaxies by using resolved star populations in a galaxy. So in our methodology, we measure the intrinsic ionizing photon production rates from individual stars, and then also spatially we measure the how many ionizing photons are consumed by the neutral hydrogen and the dust within a galaxy with a higher spatial resolution, and those numbers will provide the escape fraction. So this is a schematic plot for describing our new methodology, where in star forming regions you have a bunch of newly formed stars and then surrounded by dusty ISM. So from the individual stars stellar spectral energy distribution modeling, we can infer the intrinsic ionizing photons from individual stars. And then from the extinction corrected H-upper luminosity, we can infer the number of ionizing photons that were consumed by photoionization. And then finally, from the dust emission modeling, we can infer the covering factor of the dust for the individual star forming regions, and then we use that information to compute the number of ionizing photons that are observed by dust before escaping the first cloud. So we applied this methodology to the starburst galaxy NGC 4214, which has the stellar mass about 10 to the 9 solar mass and has the metallicity about the SMC metallicity. And then as you can see, there are large star forming complexes with transparent holes. So this system is really an excellent target to study the escape fraction ionizing photon escape process in detail. And this galaxy's FUV, absolute FUV magnitude is -16. So this was the first measurement of the escape fraction for the galaxies fainter than MUV of -19. So NGC 4214 has been emitted in multiple wavelengths with HST from NUV to NIR. And this wide wavelength coverages allow us to break the degeneracy between the stellar temperature and then dust effect effectively. So with these the NUB to NIR observations of individual stars in this galaxy, we performed the stellar SED fitting using the tool called BEAST, and we forward model the individual stars SEDs to infer the intrinsic properties of stars and the intervening dust. So I'm showing an example of one bright star fitting, and then the output of the BEAST is the 1D probability of each of the key parameters we are measuring. Using the dust column density measured from the BEAST fit, we made a spatial map of the AB dust extinction, and then focus on the one of the star forming complex in the center of galaxy. And as you can see, the dust columns are high at the boundary of the star forming region and then low in the center part. And you can see the boundaries of star forming region in the H-alpha emission line map too. So this means that the dust and the ionized gas is physically associated, and then this kind of dusty shell is created when you have a strong stellar feedback from the massive stars. So from the stellar feedback, you create a hole which the ionizing photons can escape along. Okay, so here I'm showing the local escape fraction map for the NDC 4214. So each of the individual star forming complexes or star forming regions, I calculate the escape fraction. And as you can see, some of the star forming regions have a 0 escape fraction, while the ones with the hole has the largest escape fraction of 40%. And then combining all the measurements from the individual star forming regions and considering the diffuse ISM contributions, we measure the global escape fraction for this galaxy, which is about 25%. And this suggesting that the NDC 4214 release 10 to the 52 ionizing photons per second to the surrounding IGM. And this is supporting the idea that the UV faint dwarf galaxies can provide sufficient number of ionizing photons to the surrounding IGMs. And when we did a quick comparison with the cosmological simulations, this is the NGC 4214's position on the plot. So this is really a good consistencies between the simulation and the observation. So the next step is we really apply this method to a much fainter galaxies in the local volume. So we're working on measuring the same escape fraction for the galaxies with a MUB minus 11. And this is the preliminary result of the BEAST fitting for one of this galaxy. And for the this galaxy, the intrinsic ionizing photon produced from the individual stars within this galaxy is about 5 times 10 to the 51 photons per second. And then probably this galaxy will be reside in this position within this plot. So we're working on this, the pushing down to really the UV faint galaxies to understand their role in the cosmic reionization. Thank you.
Thank you very much for your presentation, which is open for questions. So you can raise your hand on Zoom or post your question on Slack. There is one question on the Eros Vanzella. If you please go ahead.
Yeah, very nice talk. I have a question regarding the role of star clusters. I think you can identify star clusters hosted by these faint galaxies. What is the role of these young star clusters, and that probably host also the young stars that emit ionizing photons?
Yes, definitely. the star clusters are really produce lots of ionizing photons. So, for example, in NGC 4214, there is a young supercluster that are not completely resolved, even with the HST. So, but there are a bunch of observations from the literatures, and then we compare our measurement from the individual stars and then from the unresolved integrated spectra for that star clusters. And for example, that star cluster is reside in star forming region 1, and it's taking up to like 40% of the intrinsic ionizing photon production rate within star forming region 1. So yeah, definitely it's really important to take into account the contribution from star clusters within these galaxies.
Thank you.
Thank you very much. I'm afraid I think we have to move on for the sake of staying on time, but I'll invite you to post the questions on Slack and use this method to continue chatting with the speakers. So the next speaker is Grace Telford, who will speak about extremely metal poor old stars in nearby galaxies. If you want to share your screen and start right away, please.
All right. Hello, can you hear me?
Yes, perfect.
Yes, all right. Thank you very much. And thanks to the organizers for the opportunity to talk to you today. I'm going to tell you about some new observations of individual extremely metal poor O stars in nearby dwarf galaxies. Okay, so one of the key goals of upcoming JWST observations is to determine the properties of high redshift galaxies and their contribution to cosmic reionization. And as we've heard in many talks so far during this meeting, star-forming galaxies in the early universe have metal-poor stellar populations that are similar to those in dwarf galaxies in the local universe. And so to translate observations of these high redshift galaxies, which are dominated by metal-poor massive stars, into galaxy properties and ionizing fluxes, we need to use stellar population synthesis models. And so this figure is showing the many different ingredients that go into SPS models. But for this talk, I want to focus on just two key types of models: isochrones, or stellar evolution models, and template stellar spectra. And both of these model ingredients can strongly affect the inferred galaxy properties that come out of SPS modeling. But it's very important that they be calibrated against observations of many individual stars. And as I'll convince you in this talk, for massive stars, FUV spectroscopy is particularly important for this. And so at higher metallicities in the Milky Way and the Magellanic Clouds, we have a wealth of FUV spectra of O stars. And the ongoing HST Director's Discretionary Ulysses program is building up a very densely sampled empirical spectral library in the Magellanic Clouds. And so we have the data to rigorously calibrate these stellar models down to 20% solar metallicity, the metallicity of the SMC. But at lower metallicity, these FUV observations of individual stars remain very rare. And so our models will continue to be uncertain in this regime unless we get more FUV observations to anchor them. And so to convince you why these new observations are necessary, I'm going to dive into two key stellar properties that we can measure from these spectra. So in the atmospheres of O stars, metal ions absorb photons in the UV that drive winds away from the stellar surface. And different theoretical treatments of this radiation-driven mass loss predict different mass loss rates as a function of luminosity and metallicity. So the figure I'm showing here shows predictions calculated at 20% solar metallicity. And the y-axis is on a log scale. And so these two lines are showing a factor of 10 difference in predicted mass loss rate in these low metallicities. And it's a problem that our models remain this discrepant and uncertain because we need to know mass loss rates in order to correctly predict main sequence lifetimes and evolutionary pathways of these stars. And the mass loss rate also affects the emergent ionizing spectra of O stars. So the figure on the right now is showing theoretical spectra of O stars at low metallicity, where the key difference among the different curves is different mass loss rates. And so the orange line has the highest mass loss rate of them all. And you can see that the dense stellar wind very efficiently absorbs the most energetic photons that are capable of ionizing helium-2. And so to properly predict the ionizing photon production by low metallicity massive stellar populations, we need to measure mass loss rates from wind-sensitive features in FUV spectra of these O stars at low metallicities. And so different treatments of radiation-driven winds agree that mass loss rates should decrease with lower metallicity, and these weaker winds should be less efficient at removing angular momentum from stellar surfaces. So this figure is showing, again, stellar evolution models at a range of metallicities. So it's showing the rotation speed as a function of time on the main sequence. And so the blue line at solar metallicity, you can see that the rotation speed decreases over the main sequence lifetime as winds remove that angular momentum and the star spins down. But for the lowest metallicity green curve here, the curve is much flatter, so the star maintains a higher rotation speed over its main sequence lifetime. Now, stellar rotation lengthens main sequence lifetimes and changes the stellar surface properties such that they're hotter and their ionizing spectra produce more ionizing photons. And so the net effect is that rotating models like the one shown in as solid lines in the right panel predict higher lifetime integrated ionizing photon production than non-rotating models. And so we need moderate resolution spectroscopy of these metal poor O stars to be able to measure projected rotation speed from the line broadening profiles. Okay, so our team has set out to get the kind of FUV spectra that are necessary to do just these kinds of measurements at low metallicities. And so we've targeted 3 O dwarf stars or luminosity class 5 in 3 nearby metal poor galaxies that are at the edge of or just outside of the local group. So they're many times more distant than the Magellanic Clouds, so the targets are quite faint, but they're close enough that HST can resolve the galaxy into individual stars. And so we're targeting dwarf stars because they are underrepresented in existing observations. Most in the archive tend to be of supergiant stars. And these stars are still on the main sequence. And so we are getting a look at their properties during their longest evolutionary phase. And so these galaxies span 3 to 14% metallicity in terms of their nebular oxygen abundance. And so here are the new HST COS FUV spectra that we've obtained. We achieve a pretty high spectral resolution, 50 kilometers per second, and a signal to noise of about 10 with some variation across the spectral range, which is quite good considering how faint these targets are. And I've ordered the stars in order from lowest to highest metallicity from top to bottom here. And so focusing on this region of continuum between 1400 and 1500 angstroms, this area is dominated by a forest of iron 4 and iron 5 transitions. And you can see just by eye that these iron lines become much stronger going from the lowest to highest metallicity star. And in this very low metallicity star in Leo P, the continuum is essentially featureless. And so these are nice new empirical constraints on the photospheric metal opacities at these very low metallicities. And so zooming in now on two small regions of the spectra that contain features that are sensitive to the stellar winds and mass loss. I'm showing the three spectra that are normalized to a continuum level of 1 as a function of velocity offset from the bluer transition in each of these two panels. And on the right, the diamonds indicate the positions of narrow ISM absorption components, just to guide the eye. But the broad absorption features that we can see at the bottom here in the most metal-rich star, these are due to the stellar winds. And you can see they extend to pretty high velocities, out to about 1,400 kilometers per second. So we're sampling the expanding atmosphere of this star. But looking at the other two stars that are below 10% solar metallicity, we see much weaker wind features. There's essentially nothing that we can see in the nitrogen 5 line. And the carbon 4 features are shallower and don't extend to very high velocities at all, indicating that the winds become optically thin in the less dense, higher velocity outer parts of the winds. And so this is qualitatively consistent with the expectation of weaker mass loss at lower metallicity. And so now focusing on a photospheric feature, really a complex of 6 carbon-3 lines at 1176 angstroms, we can compare our observations, which are shown in black here, to model spectra that I've drawn from the TLSD O-star 2002 grid. The models have been matched to the observations in terms of the equivalent width, and rotation will broaden these features, but will not change the equivalent width. And so I can fit for the V sin I that best matches these observations. And I find that the two metal poor stars are very fast rotators. And so this seems fast, 290 and 370 kilometers per second, but how fast is that really? So for comparison, I'm now showing the cumulative distribution of V sin I in the small Magellanic Cloud, just focusing on O dwarfs similar to these metal poor stars. And I'm showing my measurements for the metal poor O stars in black, with the two below 10% solar shown as solid lines. And we can read off from this figure that these two stars are rotating faster than about 90% of the SMC O stars. And this is small number statistics. Clearly, we're only talking about 3 stars here, but I can calculate the probability of finding these two fast rotators if they had been drawn from the same V sin I distribution as is observed in the SMC. And I find that probability is low, just 3 to 6%. And so this is suggestive that these stars are drawn from a different V sin I distribution, and that higher rotation speeds are typical at these low metallicities. And I see that I am nearly out of time, so I'm going to skip the last bit and leave you with my takeaways. I've shown you evidence of weak stellar winds in these massive stars below 10% solar metallicity, and also of fast rotation speeds. And both of these effects imply longer O-star lifetimes and potentially higher ionizing photon production than would be predicted by standard non-rotating models. And so these should really be taken into account when modeling observations of metal poor high redshift galaxies. All right, thank you very much.
Thank you for this nice presentation. We have time now, short time for questions. Raise your hand or post it on the Slack, please. Is there anyone? I cannot see questions right now. Maybe I can ask a quick one. Do you when you compare with SMC features, with spectra from SMC stars, do you see a continuity with decreasing metallicity, or how is there a surprise so far in these new measurements?
I'm very glad you asked about that. So these are slides I wanted to share but didn't have time for. So yes, I have compared to stars that are matched in effective temperature, spectral type, and rotation speed to my 3 metal poor stars. And here's the comparison for our most metal poor star, the one in Leo P. And that one's shown in black. The SMC stars are the colored ones. And you can see pretty clear differences in the strengths of these wind features, right? There's almost nothing in Leo P, but very clear wind profiles in the SMC counterparts. And so this is a nice empirical, demonstration that metallicity really is an important driver of these wind strengths.
Okay, thank you very much.
Mm-hmm.
I think we have to move on. Please take a look at the Slack. There appear now some questions. Thank you again.
Okay. Thank you.
Great. And we move to the next speaker, who is Matthew Hayes from Stockholm University, who will talk about spectral shapes of Lyman alpha emission. Please take it away, Matthew.
Okay, hold on. Seems that I cannot change. Oh, I can change that. All right, thanks very much, Danielle, and for the talk. Indeed, I am going to talk about the spectral shapes of Lyman alpha in emission and how that can be regulated by the properties of the ionized gas in galaxies. So here is really a very brief overview of what I do. I have a large library of input spectra comprising medium resolution spectroscopy from HST and in the optical. So whenever you get a COS spectrum, I wait 12 months and then ingest it into my database, into my library. I begin by modeling the stellar population using Starburst 99 models to recover ages, mass, etc. Normalize and subtract the continuum from the stars. And that facilitates 3 other sets of measurements, the first one of which is measurement of the optical emission lines. So I measure up to 42 emission lines, recombination lines, and collisional lines to estimate typical nebular properties that you do quite conventionally. I measure the absorption lines of 11 different transitions in 7 different species, from carbon-2 up to nitrogen-5. And then we also use the Lyman alpha spectral database and the algorithms represented there to measure a large number of kinematic properties of the Lyman alpha emission line and numbers from there as well. So all of this together represents a pretty large database comprising thousands of measurements from Lyman alpha, stellar and nebular properties, coal gas, etc. And this was, I cannot change slides. Yeah, I can. Okay, and this was really motivated by a number of different things. First of all, the identification of these double peak Lyman alpha emitters at redshift beyond 6, where they really shouldn't exist. The universe should be too neutral, and this is probably the signpost of large ionized bubbles. Coupled with that, the sort of observation and theoretical prediction that this blue shifted Lyman alpha emission should be signpost of low column density gas or transfer through low column densities, which in turn would link to the emission of Lyman continuum, and also our own observations from last year, where we showed that among strong Lyman alpha emitters, there's no clear evidence for the evolution of profiles with redshift, meaning whatever we learn from low Z should be applicable to high Z. We also had a degree of success in modeling the Lyman alpha or predicting the Lyman alpha on a global sense from various optical emission lines. And so with JWST coming next year, it seems like a sensible study to get some of this out now while we're still in preparation. So with this very large database, we figure that it would be useful to identify some interesting questions that we can answer regarding line profiles and how we'd estimate them at high Z. This is a JWST conference, so we'll focus on optical line emission, which comes down to basically the equivalent widths in the Balmer series and O3 lines, abundances of dusts and metals, ionization or excitation parameter from strong lines, density temperature, diagnostics. So So the strategy is really to isolate relevant line ratios or tracers that will probe different ISM properties and see how well these separate out the Lyman alpha spectral properties there. And so here's the way I visualize the data. So what I've done here is to take the sample of 84 galaxies in this case and spread them by neon 3O2 ratio. So this is known to be a close correlate of the ionization parameter. Both neon and oxygen are alpha elements. They're close in wavelength, but they're not close in ionization potential. And so I make a whole lot of figures that look very much like this. So we studied the Lyman alpha emission profiles here. So these are done in stacking in different bins, 4 different bins by neon 3O2. And then we have some various other like correlation type diagrams where we look at escape fraction equivalent widths. We also look at the interstellar absorption lines in the same bins that we see over here and measure a number of properties from there as well. Equivalent widths in absorption, kinematics, etc. This is done for these carbon 2, silicon 2 lines that we show here. So we'll now go on a bit of a tour through these data. So here's kind of a more classic Lyman alpha plot, you could say. You have equivalent width on the y-axis, and it's spread by neon 3O2 on x. And first, let's look at the grayish points up here. These are the average equivalent widths in bins by this quantity, and the gray points represent like the full emission line measured over both positive and negative velocities. The red points are the contribution of just the red shifted emission, and the blue points just the blue shifted emission. So that's shorter wavelengths than line center. And so first of all, you see that there's a really strong correlation among these data points. You get, this is rho and Spearman's rho and P up here. You see very high correlation coefficients on this variable. And the solid points here are bins by 4 bins in a stack, which you see over here in the UV absorption lines of silicon 2. And you see if the Lyman alpha goes up and the ionization parameter goes up, the absorption in the continuum light goes down. And I can't see the right-hand plot because all the little windows are over it. But I have to put that somewhere else. Okay, like that, maybe. Oh yeah, and here is just showing you the how those absorption equivalent widths vary. So there's a few things to note. Well, most importantly for the sort of spectral morphology topic is that the red-shifted emission stays very close to the total Lyman alpha value. That's sort of obvious since it dominates, but that blue shifted emission really evolves quite sharply now over a much larger factor than its red shifted counterpart. And if we go on to study the kinematics, these are now, it's the same bins, the same figures on X, but now what we're looking at is moment 1 and moment 2 over here. So it's the shift of the both red and the blue peaks and the width of the red and the blue peaks. And both line features really do tell the same story here, that as the ionization parameter goes up, the lines become both less shifted away from line center, and they also become narrower, both of these being, of course, typical signatures of less radiative transfer, less broadening of the emission lines. Otherwise, the behavior seems very similar in the two, and it's indicative of there being less gas at velocities close to 0. And now we're going to turn our attention sort of quickly to the blue-red line ratio. So how much of the blue peak actually contributes to total? That starts out the lowest values in this ratio being effectively 0 and rising super sharp as you go towards the highest, sort of most ionized gas, where it contributes like 30% on the blue side. And here you see it going jump, 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 jump up in the up to normalized luminosity densities of about 0.3. So, and you see the same thing happening down here in the absorption lines, which are also vanishing as the hardness of the ionizing spectrum from the stars goes up. So this this column of absorbing gas at 0 velocity is probably responsible for keeping the lines narrow and not redistributing photons too far in velocity space, while the total column across the whole expanding envelope, out to a few hundred kilometers per second, is also lower on average, so as to let these photons then transfer. So I could go on and do this for the other things involving the other 40 one emission lines that we measure. But best is just to sort of summarize this. And we do this by showing these heat maps. And these are also, I mean, pretty complicated diagrams. We have all the nebula properties on Y up here, and Lyman alpha variables on X. These are all grouped by, again, by sort of total line overall velocity, blue shifted, red shifted emission. And then this purple, this last block over here is sort of comparing the blue and the red profiles, fluxes, which are given as flux ratios, peak separation, and these other variables. This is just for prettiness. You know, the green is showing the strongest positive correlation, the dark pink, the strongest negative correlation, etc. You can put this instead in terms of the p-value or the log of the p-value for these correlations. So, you know, just intense colors here are showing you the strongest correlation, you know, 10 to the minus 20 in some cases for some of the strongest ones. Now we're going to look in more detail at the comparison of the blue and the red emission. So we're going to zoom in on some of these values. And here's a sort of a scale bar for the color of log P over here, going to 10 to the minus 5 in the most intense colors. And if we look at the equivalent widths, for example, so here we look at H alpha, H beta, and oxygen 3. And there are some pretty convincing trends emerging here. More blue Lyman alpha emission is happening in younger galaxies with higher equivalent widths, where there's more star formation per unit mass. And that's resulting somehow in there being less gas at zero velocity. Metallicities tell a bit of the same story, but quite interestingly, dust obscuration, at least as probed by H alpha and H beta, does not work in the same manner. So what we're looking at here is something to do with the actual abundances, which might point back more to the stars than it actually does to the properties of the ISM in this case. Thermodynamic variables like temperature, density, and pressure actually tell us nothing that we can use to predict these kinematic properties of Lyman alpha, or the Lyman alpha output in general, really. Now, there's some rather interesting things that emerge when we consider the ionization parameter indicators. And here I put a whole bunch of them up. And these are listed top to bottom here by pure recombination line variables, mixtures of collisional lines and recombination lines, and then pure collisional line variables at the bottom. And these work out, for whatever reason, to be much stronger, or to correlate much stronger with the Lyman alpha kinematic property. So this is oxygen 32, the very often used line ratio, neon 302, even up to argon 4 over argon 3 is giving significant indications that we can predict the Lyman alpha output of Lyman alpha shapes. So this is sort of pointing towards a coherent picture using just the nebula line emission, not even really touching anything to do with the stars. That this quiet Lyman alpha equivalent width in these galaxies is scaling strongly with the nebula metallicity and the ionization parameter. It's all pointing back to the age, really, where the youngest galaxies give us more Lyman alpha, and it looks a bit like an evolutionary sequence, the one, in fact, similar to the one that Ran Naidu was talking about yesterday. And we also see the same sort of phenomena emerging with the escape fraction, which has nothing to do in principle with the properties of the stars. That's all gas we're looking at from that point on. And the blue-red line ratio changes similarly. And that's evolving with the blue shifted emission is evolving quicker than the red. It's indicating there's something to do with the gas covering a line center, most likely. Dust doesn't work as in the same way that the other nebula type properties do. And we clearly see the absorption lines getting weaker, exactly tracing out the sequences seen by Lyman alpha. This is pointed towards indicating, I think, that the sequence between stars and gas are really strongly coupled, and what we're seeing is what stars are actually doing to the gas. And it's running really quite quickly on timescales. It must evolve on timescales of a few mega years to describe. I mean, if we're looking at phenomenon that contemporate with the production of photons that can ionize states up to argon 4, and likely this is related to the feedback from photoionization, or perhaps the very first supernova to explode. And so the next steps for this this project, or at least to incorporate the the stellar modeling into the results. I mean, not just the optical line emission and bring direct tracking of the mechanical energy from supernova and stars. We've already counted, how much energy has been returned by supernova and things like that. We're going to continue the multi-parametric prediction work we were doing on Lyman alpha total fluxes a couple of years ago and extend that to kinematics. Going to use some other techniques to reduce all this redundant information, because it's obvious that some of these things are telling us, the same story in different words. And ultimately, the goal is to provide inputs and assist in the design and the interpretation of surveys, going from redshifts 2 and a bit and upwards out to the epoch of reionization, and ultimately optimize for what we do need to know and figure out the things that we don't necessarily. That's the full talk.
Thank you.
That's everything I had. Okay.
Thank you, Matthew. Indeed, we're quite short, but thank you for the talk. Are there some burning questions? One burning question, maybe? Raise your hand. Speak up. Okay, I think if one person wants to speak up, you have a few seconds while maybe the next speaker sets up. Xingfeng Zhu, maybe do you want to share your slides?
Yes, so let me.
I'm sorry, so
okay.
Yes, hang on a second. So I all encourage you to post questions for Matthew on the Slack, please. And sorry to move on. And the next speaker is Xingfeng Zhu from Johns Hopkins, who will talk about Lyman alpha and Lyman continuum escape from magnesium to galaxies. Please take it away.
Okay, thanks for the intro. So I'm Xingfeng. Today I'll talk about tracing Lyman continuum and Lyman alpha from magnesium to emissionize. So the outlines are straightforward. I will begin with the introduction and sample selection. Then I will talk about what can we learn from magnesium to emissionize. Then finally, I will talk about the correlation that we found for between magnesium 2 and Lyman alpha and Lyman C. So a few sentences for the introduction. As we all know, direct Lyman continuum detections at higher Z is impossible due to the neutral IgM attenuation. So therefore, this requires indirect indicators for Lyman C or lower redshift. And indeed, in the past decade, various indirect indicators have been developed. And I show some of the top ones here. I also highlight people's talks from yesterday and today about each of the topics. For example, from Lyman alpha, UV absorption noise, high O32 values, and super 2 deficiency. Among them, one of the leading one is Lyman alpha. Given a resonant 9, Lyman alpha profile embeds information of neutral hydrogen. And one of the concerns, however, is that Lyman alpha would suffer from neutral IgM and a higher Z, and the interpretation would become complex close to the epoch reionization. So that's why we want to study another indirect indicator. Some of the people may already know is magnesium 2 emissionize. And the magnesium 2 is a doubleted emission at around 2800 angstrom, and have been suggested to be a good Lyman alpha and Lyman C tracer. For example, from the Henry 2015-2018 paper and Chisholm 2020 paper. So given an ionization potential of 15 eV, which is close to 1 Rydberg, it can be used to trace the neutral hydrogen. And similar to Lyman alpha, magnesium 2 is also a resonant 9, and it is also a double 9. So the 9 profile not only contains the information about the geometry of the H1 column density, but also contains information about the optic depth of magnesium 2. I will explain them later in the slides. And magnesium 2 has a longer wavelength and much less attenuated by the neutral IgM, therefore make it a good candidate for upcoming JWST observations. Okay, so what do we study here? We mainly study 8 galaxies with new observations selected from STSS with strong magnesium 2 emissions. They're equivalent with larger than 10 angstroms. So each galaxy have new HST cause G140L, G160 observations, except one of the galaxy we took from the LZ-LCS survey. So each galaxy also have optic spectral from STSS that covers the magnesium 2 regions and also O32 regions. Then half of the galaxies we have Lyman C detections with larger than 3 sigma significance. So the detection rate 50% actually very high. So then what can we learn from magnesium-2 emission lines? So we show here in the top row the Lyman alpha for 4 of our galaxies, and correspondingly in the bottom row we show the magnesium-2 regions for these 4 galaxies. The blue and red are for the 2 doublet of magnesium-2. And what we expect is that the flux ratio of the magnesium-2 is correlated with the object depth of magnesium-2, also shown here in the right panel, where the flux ratio is showing on the right axis, and the blue to red flux ratio, and then the x-axis is object depth of the red doublet. When the flux ratio is approaching 2, then the object depth is around 10 to the -3, very small. And then when the flux ratio is approaching 1, then the object depth is also approaching 1, or 0.7 actually. So for all of our galaxies, obviously we can see all have the blue doublet is much stronger than the red doublet. Therefore, the object depth of magnesium-2 is very small, less than 0.7 or even more less. So the cloud is object the same to magnesium-2 for these galaxies. The second thing we can learn is the column density of neutral hydrogen from the column density of magnesium-2. So we do so from photonization models from clouding. So the x-axis here is the total hydrogen column density into the cloud. So basically from left to right, you are going deeper and deeper into the cloud until you reach the hydrogen strong green sphere, showing as the dashed lines. And then the y-axis is accumulated column density for different ions, for example, oxygen 2, oxygen 3, and then the magnesium-2 in red and neutral hydrogen H1 in black. For H1 with -4.0, just to shift it down here. So for the orange line, we show the position where the neutral hydrogen column density equal to 10 to the 17, which is around the transition point where the cloud becomes object sick to the ionizing photon. Then obviously we found these 2 curves are parallel, magnesium-2 and H1. Therefore, for large parameter space, we can use the column density of magnesium-2 to trace the column density of H1 until they reach a very deep cloud here. But we don't expect to see much ionizing photon escape from these regions. Okay, then if we truncate the model at different depths, we can then study magnesium-2 at different bounds. For example, if we truncate the model here, we can study the density boundary regions. If we truncate the model here, we can study the ionization boundary regions. So that's how we study and estimate the magnesium-2 escape fractions, is shown in this figure. So this is constructed from a large grid of cloudy models. X-axis O32 flux ratios, y-axis magnesium-2 flux divided by oxygen-3 flux. So they are all predictions from clouding. The different colors for different ionization parameters and 2 different symbols of 2 different boundary cases. And we can see for each galaxy, as long as we have their O32 flux ratios and also the oxygen-3 flux, we can get the intrinsic magnesium-2 flux from these correlations. And then with the observed magnesium-2 flux, we can then derive the escape fraction of the magnesium-2. And one of the important things is this correlation is consistent for both boundary cases. You can see the different symbols only shift the results along the line. Therefore, we don't have to know the exact boundary case for magnesium-2 when we derive its escape fractions. Okay, so finally, I will show the fun part, the correlations between magnesium-2 and a few other things. So first of all, I will show the magnesium-2 with O32, while the y-axis is the derived escape fractions of magnesium-2, and then the x-axis is O32 values. Our 8 galaxies are shown in red. We also show a comparison samples taken from the literature. So these galaxies have moderate single-Lois magnesium-2 detections, are shown in green. And they are from, for example, LCS, Izotov et al, and Henry et al, and Garcia et al. So obviously, there is a tight positive correlation here, and some of the galaxies look like saturated when they have very high O32 values. And then we will compare magnesium-2 escape with Lyman alpha escape in the y and x axis. So first of all, we can see there is a tight correlation. Most of the galaxies follow a tight trend here, and some of them just off the trend when the F escape Lyman alpha become very large. And we also compare 2 curves from different density extinction laws, showing these 3 different curves here, and they assume non-resonant scattering. But recall, both magnesium-2 and Lyman alpha are resonant lines, So what we expect is, we expect that the FAC gamma alpha should be always less than, or usually much less than the escape fraction of magnitude 2, because gamma alpha's optic depth to resonance scattering is much larger. But what we saw here is the best fitting correlation. You can see, or you can see directly from the figure, is they are of the similar magnitude, the escape of magnitude 2 and gamma alpha, or off by like factor of 0.8. So this suggests that the path lenses of these two resonant lines are actually very similar, not like what we expect. They are much smaller in gamma alpha. So this may be because the magnitude 2, as we found from the doublet line ratio, they escape from the optically thin channels. And if gamma alpha also escape from that channel, then the path length could be very similar. Okay, so the last thing I want to show is the correlation between magnitude 2 and Lyman C. So we adopted a method shown in Chisholm 2020 paper, and we predict the FA escape Lyman C using magnitude 2 emission lines and dust extinctions. So due to lack of time, I won't show the detailed duration, but you can refer to this paper. There are two important points here. One is the cloud is optically thin to magnitude 2, which we already confirmed it from our doublet line ratios. And another is the column density of magnitude 2 can be used to trace the column density of H1. We also show it from clouding models. So the x-axis is predicted FA escape Lyman C from magnitude 2, y-axis is measured from the XED fittings. So the results is we found obviously there is a positive correlation, but with some of the scatterings here. But recall, most of our galaxies shown here only have STSS object spectral for magnitude 2 regions. Therefore, future higher single noise observations can constrain these correlations better. And we actually already have these data in hand, mainly from MMT and extruder. So we plan to work on it in early next year. Okay, that's all I have. And the brief summary is listed here. And I also look forward to see more magnitude 2 spectral at high redshift, and also from JWST for redshift around 2 or so. And then yesterday also, actually Naidu already showed from their extruder observations, they already did stacks of magnitude 2 for leakers and non-leakers. You can see for leakers, their magnitude 2 profile, the blue is much larger than its red doublet. This hint, as we suggested before, the magnitude 2 is optically thin here. And for non-leakers, these two doublets are very similar, which means the magnitude 2 is much more optically thick than the non-leakers. These findings are actually very similar to what we saw in the low redshift galaxies. Okay, that's all my talk today. Thanks for listening. Any questions?
Thank you very much, Yinfeng, for the nice talk. We have time for questions. Please raise your hand or post it on the Slack. Don't be shy. Yes, we have a talk from Yuri Izotov, who says, nice talk. What do you expect is a typical signal to noise ratio you would need on the magnesium 2 doublet to accurately predict the Lyman continuum escape fraction?
Currently, okay, for STSS, currently we set the, in our sample, signal noise ratio is larger than 3. So we think it should at least be larger than 5. The major reason is we need to have the doublet line ratios. And it depends on, usually you can see for these leakers, the red doublet is much smaller than the blue. And if the red doublet is like half of the flux of the blue one, then you need 4 times the single noise, right? Then it depends on the red doublet, the weaker the red doublet, the higher single noise you want here. So.
Thank you. There is another question from Yuri Mattia on the Slack, who says also a really interesting talk. And he's wondering about the method to infer the escape fraction from magnesium 2. In particular, how do you convert the magnesium 2 column density to H1 column density? And how do you know the magnesium to hydrogen ratio in the gas?
Okay, yeah, so it's a good question. So I already show here. So from clouding model, we found the two curves, the column density of magnitude 2 and the column density of H1 parallel with each other. So they differ only by a constant for a certain magnetic. So we assume the magnetic of this magnitude 2 cloud is similar to the gas phase magnetic we measured from the nebular lines. That's the assumption we take.
Thank you. Another question from Renske Smith, who says, thanks for the talks. Are there more simple diagnostics that can be measured with NIRSPEC prism spectroscopy, such as the equivalent widths of the magnesium-2, which would have any predictive value for the Lyman alpha and Lyman continuum?
Yes, we also, let's see if I have the equivalent width plot here. I don't have the in the slide. In the paper, we are in the completion of the paper now. So in the paper, we show the equivalent width of magnesium-2 compared with the equivalent width of Lyman alpha. Definitely, there is a positive correlation here. So if you have the equivalent width of magnesium-2 from the spec directly, then you can derive the equivalent width of Lyman alpha here, and they may be correlated with the escape fractions also. Yeah.
Excellent, thanks. If there is a last quick question, we can take it. Maybe, if not, we thank you again, and we thank all the speakers of this session. Please stay with us. We have now 10 minutes for lightning talks. So 5 short presentations. The first will be Tae-Sung Kim from Yonsei University. Please go ahead.
Hi, can you hear me?
Yes, thank you.
Okay, thanks. Hi, I'm Tae-Sung Kim from Yonsei University, and I'd like to briefly introduce our ongoing efforts to understand the propagation of Lyman continuum and Lyman alpha photons. As many of you agree, we are not fully sure how Lyman continuum photons are observed and Lyman alpha photons are scattered in galaxies. So in order to understand this process in detail, we have been working on RMHD simulations of GMCs and try to measure the escape fractions and line properties such as velocity separation or flux ratio between the blue and red wave. So if you're interested, please check our paper recently posted on arXiv, and I'm happy to discuss anytime. Thank you.
Thank you very much. I think we can move to the next lightning talk by Patty Boland from UC Davis.
Hi, can you hear me?
Yes, perfect.
Okay, awesome. So hi, I'm Patty Boland at UC Davis. So basically the work that we've been doing is inferring the IgM neutral fraction at 2 high redshifts during reionization, 6.7 and 7.6. So the way that we're doing this is we have really large samples of faint Lyman break galaxies. So in the bottom left, you can see the distribution. Our median luminosity is 0.1 L star. And what we do is we compare the Lyman alpha equivalent width distribution, including upper limits from non-emitters at these high redshifts to a baseline redshift of redshift 6, where the universe is thought to be ionized. And then we compare to realistic IgM simulations. And from that, infer a neutral fraction by assuming that the difference between the Lyman alpha equivalent width distributions is due to IgM attenuation. So in the end, in the bottom right panel, our final results are the orange stars here. So an upper limit at 6.7 of 25% and a neutral fraction of 83% at redshift 7.6. And this should be on the arXiv tomorrow, I believe.
Thank you very much. Next lightning talk is by Santosh Harish by Anthony Taylor from University of Wisconsin.
Hi, I'm Anthony Taylor from UW-Madison, and my poster is on the evolution of the ultraluminous Lyman alpha luminosity function near the epoch of reionization. In brief, using a large narrowband survey in the north ecliptic pole, my group has identified 21 Lyman alpha emitters, and we've spectroscopically confirmed them all using DEIMOS. And in producing luminosity functions from this sample, we've noticed an interesting phenomenon where the luminosity function at the faint end seems to have significant evolution from redshift 6.6 to 5.7, but we see a convergence at the bright end. And we believe this may be evidence for these Lyman alpha emitters forming ionized bubbles around themselves toward the end of reionization, and at the very bright end becoming visible earlier. If you'd like to see more details, please stop by my poster thread or the breakout room. Looking forward to a great discussion.
Thank you very much. The next short talk is from Santosh Harish from Arizona State University.
Hi, can you hear me?
Yes.
Okay, thanks. Hello, everyone. I'm Santosh Harish. I'm a final year grad student at Arizona State University, advised by James Rhodes and Sangeeta Malhotra. I'm here today to advertise my poster highlighting results from a recent work looking for AGN signatures in green pea galaxies. Thanks to numerous talks that have discussed green peas, I'll skip introducing this special class of emission line galaxies, but just emphasize that in the context of reionization, green peas are one of the best analogs of high-redshift galaxies that one can study. So apart from this strong O3 emission, the optical spectra of many green peas contain some ionization lines such as helium-2 and neon-3, which indicate the presence of a hard ionizing source. The BPT diagram classifies these sources as star forming. However, the important question is to what extent are these purely due to star formation and whether this could be due to accretion in an AGN. So motivated by these questions, we explored green peas in the mid-infrared to look for AGN signatures, since hard dust emission due to AGN can be distinguished from star-forming galaxies using mid-infrared colors and variability. And we find a good chunk of green peas with rarer colors, as shown in the middle figure, and some showing variability, example of which is shown on the left figure. You can learn more about this work in my poster, so please feel free to stop by and ask questions. Thank you.
Thank you very much. The last short talk is from Asuka Igarashi from Tsukuba University.
Thank you. So we constructed a new galactic wind model and estimated the mass flux from the observed wind velocity. As shown in the left figure, we compare our model to the commonly used the shell model. For massive galaxies, the mass flux over SFR is smaller than the shell model. Our result is consistent with the prediction by cosmological simulations. And next, we applied our model to the HeII galaxies. As shown in the right figure, the mass flux over SFR correlates with the rotational velocity independent of the redshift. That's all. Thank you.
Thank you very much for all the lightning talks. I think we can break now. So as you see in the background, and you will see there are different breakout rooms now, to which I invite you, where I invite you to join some of the speakers. And then after a break, we will reconvene in basically 23 minutes from now for the session 1D. So I wish you all, thank you again for all the speakers and all the poster presentations. Please use the Slack again to interact and chat, pose your questions, and see you in the breakout rooms, and enjoy your break. Thank you.
Hi, Yichi, are you there?
Hi, Crystal, I'm here.
Hi, how are you?
Yeah, I'm doing well.
Nice to meet you, I should say.
Nice to meet you. Yeah.
So I caught the end of the lightning talks there.
Okay.
What do I need to, obviously I need to introduce the speakers. Do I need to do anything as far as giving them access to Zoom, or?
I think like for the second half, Yuki will switch over from me, but I can explain. Basically, okay. Yeah, we'll hand over the co-host to all the speakers in the afternoon. And okay. We're going to show the clock that you probably already have seen.
Yes.
So there's a presentation clock, but the sound, sadly, it doesn't work. So, but everyone can see it. So maybe it's the chair's choice to whether to make a notification to the speaker at some specific time, or when do they want to do it. So it's up to you if you want to warn them
Okay.
if they're going too long, but that clock is just for reference. So.
And just so I get this clear, are we taking any questions right after the talks, or is this all for the Q&A sessions?
Well, I think it's every speaker has 15 minutes, but well, like in the past sessions, usually it's 10 minutes plus 5 minutes Q&A.
Okay.
So
Perfect.
there can be a couple of questions, and people can raise their hands in the Zoom room, or you can read the comments or questions from the Slack channel.
Okay. So, yeah. That makes sense then. And I can, if I want to talk to the speaker ahead of time and make sure I've got their name pronounced right and tell them when I'm going to give them a warning about time, I can go find them in one of the Zoom rooms.
I think they should, yeah, they should be here. I don't know. Yeah.
Or can I use the Zoom chat to talk to them directly, or?
I think during the break, you can test for every speaker whether their screen share is properly working or not, and maybe chat with them. And well, I can, if any of the speakers are in the breakout room, I can get in there and they ask them to get back. But yeah.
Well, yeah, and it's still a few minutes early right now. So in principle, they should join this main room that we're in another 10 minutes or so, or they'll be in a breakout room is what I'm missing, I guess.
Yeah, but first speaker is here now. So
hi, Yuri.
Yeah, hi, Kristan. Yeah. I think that I'm co-host. Yeah, I can start presentation. Yeah.
I think everyone's going to need to test that they can share. So why don't you go ahead and do that?
Okay. Do you see it?
I see it. Now,
great.
Are you going to go? I see the mode with like one central slide and then all the small slides on the left.
Yeah, I tried before, and my presentation is too large, and it's not does not fit the screen. But what is about size is now?
That's much better. It's.
Do you see everything?
I see all the references at the bottom, and I see the full lines from left to right.
Yeah, and okay, I can. Oh, do you see everything? Yeah, I see.
Well, of course, I don't know what I'm not seeing, right? But
well, yeah, but
okay. Now hold on. Go back. Go back.
Yeah.
Okay, there's a little bit cut off at the bottom. I'll tell you what. If you go back.
Here.
No.
Here?
That's okay. One more. Still good.
No,
still
nothing.
Good.
Nothing.
But up at the beginning, there was something cut off on one of. Okay, go forward. You good? That one's okay. Good.
Well, everything is fine.
That's good.
Yeah.
I thought I saw a label cut off one of them.
Well, level edge of left edge of right edge of bottom.
When I saw a little bit cut off, it was at the very bottom of the slide.
Okay, but probably I moved too fast. Yeah, so now it's okay. Okay.
It looks good now.
Okay, so I can stop with this.
Super. I'm really excited to hear this. And it's Izotov, is that the correct pronunciation?
Yeah, you can. Yeah,
close enough that you're happy? Okay.
Yeah. Okay, I stop now. So to check other speakers.
So Yuri, I'll plan. It's a 10-minute talk and then 5 minutes for questions.
Yeah, you know, yeah.
Do you want any kind of warning during the 10 minutes, or the clock will appear?
Well, I will check the clock. Yeah, so I will try to be on time.
Okay.
Well, actually, not really, not exactly 10 minutes. I don't know, but it's total of 15, and sometimes there are time for a couple of questions. So
yeah,
anyway,
but
it's okay.
You cannot predict how many questions.
Yeah. Well, that's decided by the chair. So yeah.
Yeah.
Yeah, I'd like to. I mean, I think it helps, especially on Zoom, to have a little bit of interaction with the questions. So. If we're not done at 10, I'll be waving at you or yelling at you or something to finish up. Okay, have any of the other speakers for session 1D joined us?
I'm the fourth speaker. Can you hear me?
Yes. And then is it, help me with the pronunciation, is it Mattia?
Is Mattia.
Mattia.
Longer E. Yeah.
T-E, and then, okay, I'm going to guess here Sirressi, but maybe one of those vowels is long. Sirressi.
That sounds really good.
Okay. Mattia. Okay, Mattia, do you want to try to share your screen and put your presentation up? We can check that that works.
Yeah, I can try. So now you see all the slides, right?
Yes.
Okay, and this is the presentation mode. Does it look good?
It looks good.
And I can change slides.
Yes.
You see all the slides, right?
Oh, I see beautiful pictures. Yes.
Oh, perfect. And my video. Okay.
Yeah.
You can see my video as well.
Yes.
Okay. Then it's I will change location, but right now I'm in the office with other people.
Okay.
Yeah. Thanks.
Mm-hmm. So Mattia, the sun is setting for you, or just set? Is it is still yet to rise for me?
The sun is setting because I'm in Sweden.
Yes, that's good. It means it's coming this way. It's still pitch black outside.
Wow. In which part of the US are you?
I'm in California, so.
Okay.
We're
Then it's the farthest.
behind. Okay, do we have any other session 1D speakers online so we can?
Hi, Kristan. This is Yuichi.
That was Yuichi, yes.
Yes.
Hi.
Hi. So can you try my share screen?
Please.
Yes.
Are you in Japan or London?
Now in Japan.
Excellent.
Yeah. So now I hope you can see my screen.
You can.
Okay. Then slide moves properly. Probably.
Yeah.
Okay. Good.
I see the bottom line and the Inslee reference, so I think you're.
Okay. Good. Yeah. Okay. Perfect. Thank you.
Mm-hmm. And then Mattia and Yuichi, we're kind of aiming for a 10-minute talk, 5 minutes of questions. Do you want any kind of warning as we approach 10 minutes?
For me, I think you can go ahead.
Oh, sorry. For me, maybe if I'm running really late, you can tell me, but I should take around 10 minutes. So
okay.
A warning should not be needed.
Okay, if we get to 10 minutes, and it doesn't seem like, you're within a sentence of finishing, I'll say something about the question time. And there's, in the Zoom, at least on mine, you can see a presentation clock that shows the time pretty clearly. So that's nice.
Yeah, for me, I think we can see HeII is clock, so yeah, warning maybe not be needed.
Great.
Yeah.
That's kind of what I was thinking. It seems just distracting to say anything when you're just speaking for 10 minutes. Good.
Hi, Crystal. This is Kristan here.
Hi,
Do you mind if
Kristan.
I test sharing my screen?
No, please do. And your last name, is that Boyett?
Yeah, perfect, Boyett.
Boyett, okay.
And how's that?
Looks good to me.
Perfect. Okay, cheers.
And Kristan, we were saying we're looking at 10-minute talks, 5 minutes for questions. I'll probably just let you can see the presentation clock. So if it gets to be 10 and it doesn't look like you're about done, I'll point that out to you. But otherwise, I won't interrupt the talk to tell you that it's 8 minutes or something.
That's brilliant. Thank you.
Okay.
Hi, Crystal.
Yi, hi.
Yeah. Hi. Nice to meet you.
Yeah. Yi, is your last name pronounced Zhu?
It's actually she, but I don't really care about the pronunciation of my surname. People usually just call me E.
Let me try. So it's E.
I can go.
E Shu.
Yeah, I can go with that. Thank you.
Okay.
And yeah, I guess I should share my screen.
Yes, please.
Now let me turn my presentation on. Can you see my screen?
Yes.
Yes, I guess it's perfect.
Nice background too.
Really? It's just white.
Oh, I saw, maybe that's a Zoom thing. I saw these like purple mountains.
Oh, that's maybe my desktop.
Your desktop, yes. Not the standard Apple desktop.
So yes, I guess that's it. I'm aware of the clock thing, so feel free to remind me if I'm exceeding too much.
Yeah.
If you need it, but I will keep it around 10 minutes.
Yeah, so try to aim to finish in 10, and then you can see the presentation talk. If it's running past that, I'll do my best to cut you off so that we can have some time for questions.
Sure. Thank you.
So has Yuki joined us?
Yes, yeah.
Hi, did I pronounce that right?
Come again, please.
I'm not sure I pronounced your name right. Is it Yuki?
Yes, yeah.
Oh, so I got it right. Good. When the talks are done.
Yeah, actually, yesterday.
Okay. I guess I'm wondering, after Ishu's talk, we have the break interaction and posters.
Exactly.
Do I need to do anything to facilitate that, or you've got that all under control?
Nothing special, yeah.
Just tell people that they can go to the breakout room to discuss with people.
Yeah.
And people will be at their. So then there's a separate room for the poster people. Is that the way this works?
Yes, yeah. We made the breakout rooms for the all presenters today. So maybe all the participants go to the each breakout room.
Okay. And then after 20 minutes on the schedule at 16:05, we have adjourn. People, I mean, but then it says one can continue discussions in the breakout rooms. Am I supposed to officially say something to close the session at that point, or do we just let things drift off in the breakout rooms?
Yesterday I remember Masami announced the close at the main room only, but
Well,
Masami, did you remember that? Or Yechi, do you remember that?
I think by the end of the second session, the chair would just say, now the breakout room is open, and then we'll prepare the breakout room, make it open so everyone can do discussion. And well, when the clock clicks 16:05, we'll just let it fade away. We make an announcement here and we broadcast a message saying, well, that's all for today, but you can continue discussion. And yeah, that's what we did yesterday.
Okay. So I should make that announcement at 16:05, or that's something you guys want to do?
Well, we can do it if you want.
I'm happy to do it. I'm just trying to make sure I do the right thing.
I think Yuki is the host now. Maybe it's more convenient for him to send the message to everyone, I guess.
Okay.
Yeah, I will do that. Yeah.
Sounds good. So Yuri, why don't you go ahead and start your screen share right in another minute here. I'll say a word or two, but
okay.
Might as well be ready to go.
Mhm.
All right, welcome back everyone to early galaxy formation near and far. Our first speaker in session 1D is going to be Yuri Izotov, who's going to tell us about local compact star-forming galaxies as analogs of high redshift galaxies. Take it away, Yuri.
Yeah, I do not see my presentation.
Neither do we.
Okay. Do you see it?
Do not.
Sorry about that. Can you try again, please?
So, sorry?
Please try again.
Okay.
To share.
To share? Or start presentation, what?
Please try to share your screen.
Ah, to share, okay. Okay.
Okay, we have it, and you just need to start presentation mode.
Mm-hmm. Okay. Oh, it's too large, yeah?
It's a little bit cut off now on the
Okay.
sides, which when we
So,
tested it
okay.
earlier, it didn't have that problem. So I'm not sure
Okay,
what changed.
let me do it this way, yeah? Okay, thank you. So I will discuss properties of local compact star-forming galaxies and compare them with the properties of high redshift galaxies at redshift 2 and above. Results of the study have been published in 2 papers which were appeared recently. You see these papers here. And so we call these galaxies compact star-forming galaxies because of selection criteria which we applied. So first of all, we adopted equivalent width of first beta emission lines above 10 angstrom, no sign of AGN activity, angular radius below 3 arcseconds. So you see on SDSS image, it's very compact. And the same image with the HST of the same object shows that it's even more compact. We use the data release 16 of the Sloan Digital Sky Survey and selected 25,000 of compact star-forming galaxies. And then we derived as many properties as we can from spectra and from photometry. Other names of the subsamples of this sample can be called sometimes blue compact dwarf galaxies, green peas, luminous compact galaxies, blueberries, but these are parts of this sample of compact star-forming galaxies. And common for these galaxies is that they have compact size, low mass, low metallicity, active star formation. Some compact star-forming galaxies have extreme properties which are not known yet for galaxies at high redshift. Here I show one example of this galaxy. The galaxy has extremely low metallicity, oxygen abundance 7.09, O3 to O2 ratio is 53. Extremely high equivalent width of H beta, 577, and very high number density, very dense H2 region with number density about 1000, and very low mass to luminosity ratio. Additionally, we detected in this galaxy helium-2 4686, suggesting this implies the presence of hot ionizing radiation. This low mass to light ratio 100 is typical for a zero-age instantaneous burst, and this implies that probably in this galaxy we have no underlying older stellar population. But of course, it could be studied in more details. On the SDSS image, it's very compact and the linear diameter is less than 1 kiloparsec. However, for the most of galaxies, the properties are not so extreme. And here I show distributions of different important parameters for this sample. Stellar mass, absolute magnitude in UV, oxygen abundance, equivalent width of emission line 03507, 03202, and specific star formation rate. All these quantities are similar to objects observed at redshift 2 and higher. And in particular, roughly 1,500 complex star-forming galaxies have equivalent width of O3 line above 1,000. So it's a large sample for study. So this sample can be used and is used to solve different problems. Okay, first one is element abundances, including primordial helium abundance. So then integrated characteristic. ISM in using UV spectra, so different emission lines originated in the interstellar gas and absorption lines. Also, massive stars at low metallicity can be studied in some of these galaxies. We already detected O6, nitrogen 5, Wolf-Rayet, LBV, and some other features of massive stars. I suppose that should be at low metallicity. So then origin of ionization species in many galaxies, helium-2 emission is observed, and in some is even neon-5 emission is seen with ionization potential, which almost twice higher than ionization potential for helium-2. And of course, escaping Lyman cell radiation. So in principle, this properties can be applied for high redshift objects, but we can be sure that these high redshift galaxies have similar properties as local galaxies. So to check this, we use as many characteristics as possible. This is stellar mass, luminosity, star formation rate, specific star formation rate, emission line fluxes, and equivalent widths of strong emission lines. O3 to O2 ratio, neon-3 to O2 ratio, UV slope, ionizing photon production efficiency. And now I start with the BPT diagram. It was suggested in many papers that high redshift galaxies deviate from zero redshift galaxies. They have either enhanced O5, O3 line, or nitrogen 2 line, or both. So, and it's seen in this diagram, the two sequences, green and yellow, the sequences from two different papers for high redshift galaxies, and cyan sequences for local sequence of galaxies. But however, if you look on this inset in this figure, you see that our galaxies, which are shown by blue and red, blue objects with equivalent width above 100 and red below 100, all blue galaxies and large fraction of low objects with lower equivalent widths are also above the main sequence for redshift 0 galaxies. And they are in good agreement with high redshift objects. Their location is good in agreement with high redshift galaxies. Another diagram O3 to versus R23. This diagram actually this quantity which determines ionization parameter and oxygen abundance. You again see that our object blue and red points are in agreement with the sequence obtained for high redshift objects. However, I would like to know that in this sample of local star-forming galaxies, we also determined the sequence of extremely metal-poor star-forming galaxies on both diagrams, which strongly deviates from the sequences obtained for the most of local star-forming galaxies, compact star-forming galaxies. Here I show some relations, some popular relations which are used for analysis of high redshift objects. These are dependencies on stellar mass of UV luminosity, star formation rate, specific star formation rate, and O3, 507 emission line flux. Again, our objects, local compact star-forming galaxies are in blue and red, and by black dots are shown high redshift objects with redshift above 2, and also some color lines also show some dependencies for some papers. You see that high redshift objects in good agreement, the location with location of galaxies, compact star-forming galaxies with equivalent widths above 100, and large fraction also of galaxies with equivalent widths below 100. And actually, this part, these galaxies can have equivalent widths below 50. Angstrom, and if you put cut not 10 but 50, all these objects will disappear from these diagrams. And again, extremely metal poor galaxies are off, and also they are very low metallicity objects. Here, another dependencies, O3 to 2 stellar mass, and also equivalent width of O3 line on stellar mass, and some combinations of stellar mass and star formation rate. Everywhere you see very good agreement between location of low redshift and high redshift star-forming galaxies. And here is ionizing photon production efficiency. Again, we see the same, and also we see that considerable fraction of compact star-forming galaxies have ionizing photon production efficiency above the canonical value, which is used for calculations of reionization of the universe. And also we may consider many more relations. However, all this consideration leads us to conclusions that the properties of nearby compact star-forming galaxies are very similar to many known properties of high redshift galaxies at redshift above 2. And we actually do not find any differences between these two types of objects. And then we conclude that compact star-forming galaxies could be a very good local analogs of the high redshift objects, and all studies which are conducted for low redshift objects can be applied for analysis of high redshift objects. So I finished. Thank you.
Okay, thank you, Yuri. We have just a few minutes for questions. I encourage you to type them into Slack, into the Q&A session. or to raise your hand. We're more likely to get to it in Slack, but we could take maybe one by a raised hand. I'll take the prerogative of asking the first question. I'm curious, Yuri, in the diagrams where you compared to high redshift galaxies, the BPT diagram, for example, where there's overlap between a nearby analog and a high redshift galaxy, are they offset in terms of their stellar mass? Are the nearby galaxies that look like high redshift galaxies of much lower stellar mass?
Well, probably it's better seen here where I show dependence on the stellar mass. Actually, diagrams for low redshift objects are broad, so it continues to lower stellar masses compared to higher redshift galaxies. But anyway, there are some consider a fraction of high redshift objects with stellar masses 10 to 7, 10 to 8, so it's really dwarf systems.
Okay, so the length of the line there for the high redshift galaxies is actually...
Well, it's mainly, we compare these properties of ionized radiation, so it's emission line strengths, it's not directly masses.
Okay, great. Thank you. Thank you. An excellent talk. We are out of time for questions. I'm going to ask Yuichi Harakani to set up his slides. And if there are further questions, you can enter them in the chat for the Q&A on Slack. Thank you, Yuri. There'll be another opportunity later to join Yuri in a Zoom room to ask further questions. Our next speaker is Yuichi Harakane, who's going to talk about early galaxy formation probed with the most extreme line emitters at redshift 0.8.
Okay, so hello everyone, I am Yuichi Harakane from University of Tokyo. So today I will talk about the most extreme line emitters at redshift 0.8, and especially I will discuss the physical origins of the high equivalent width objects in high redshift universe. So recent observation shows that high redshift galaxies, for example, the redshift beyond 6, shows the strong O3 emissions. So galaxies at the epoch of the reionization shows a high O3 equivalent width of about 200 to 6,000 angstrom in rest frame. So for example, this figure shows the spectral energy distribution of a galaxy at redshift 6.8. And here you can find this prominent IRAC excess indicating that the O3 equivalent width is about 4,000 angstrom. So these galaxies, these strong O3 emitting galaxies at the epoch of the reionization are thought to be young and metal poor galaxies. However, we don't have definitive conclusions for the nature of these galaxies due to the limited sensitivities and wavelengths of the current telescopes. Okay. So instead, people are studying the analogs of the high redshift galaxies in local universe, such as green peas. So this figure in the right panel shows the O3 equivalent width as a function of the stellar mass, and you can find that there are some galaxies showing the O3 equivalent width of about 1,000 angstrom at the redshift from 0 to 2. Okay. However, there are no galaxies with O3 equivalent width larger than 3,000 angstrom, although there are such kind of extreme galaxies at the epoch of the reionization. Okay. So in order to understand the nature of this kind of extreme line emitters at the epoch of the reionization, we want to study galaxies located here. So in this study, to understand the nature of the most extreme O3 emitters, in this study we focus on two O3 emitters at redshift 0.8. So these galaxies, these O3 emitters are identified in the Subaru hyperspectrum survey, and O3 equivalent width is about 5,000 to 6,000 angstrom. Okay. H-beta equivalent width is also 700 to 900 angstrom. And in these two bottom panels, I show the O3 and H-beta equivalent width as a function of the stellar mass. And these galaxies are located in these very unique regions compared to the previously studied galaxies. Okay. And these O3 equivalent width is comparable to some of the some of the extreme high-redshift galaxies. So in order to understand the physical properties of these extreme galaxies, we conducted a deep spectroscopy with focus and Keck-Mosphere. And here I show the focus spectra for these two galaxies, ID1 and ID2. And of course, not only the strong emission lines, but also we detected faint emission lines such as 4363 auroral lines here. Okay. Also, in one galaxy in ID1, we detected helium-2 emission lines. Okay. Also, Keck-Mosphere observation shows that in these galaxies, the nitrogen-2 and sulfur-2 emission lines are very weak. So in these two panels, I show the nitrogen-2 and sulfur-2 emission lines in ID2 and ID1 respectively. And you can find that there are almost no detections or very weak tentative detections. So this indicates these two sources are classified as star-forming galaxies. So here I show classical BPT diagrams, and these two sources are located in the star-forming regions, not AGN. Okay. Then, as I explained before, we detected 03, 4363 auroral lines in both of the galaxies. So by using these 03, 4363 line, we can estimate the gas phase metallicities by the direct temperature method. Okay. And the estimated gas phase metallicity is about 0.07 solar to 0.2 solar metallicities. Okay. Then we investigate whether this subsolar metal gas phase metallicity can explain the observed O3 equivalent width. So in these two panels, I show the O3 equivalent width and H beta equivalent width as a function of the stellar age. Okay, and the observed equivalent width of ID1 and ID2 are shown in these red and magenta shades here. Okay. And this red and this orange line are calculations based on the cloudy photoionization models. So here I assume the gas phase metallicity is equal to 0.2 solar. This is constrained by our direct temperature method metallicities. Okay, and we also assume that the stellar metallicity is same as the gas phase metallicity. Okay, and you can find these two lines, solid and dashed lines. Okay, the solid line is calculation based on the IMF from 1 to 100 solar mass, and dashed line is a calculation based on the IMF from 1 to 300 solar mass. So dashed line includes more massive stars. So as you can see, with these both models, these models can explain the H beta equivalent width within these errors. However, these models cannot explain the O3 observed very high O3 equivalent width. Okay. So next we consider very low stellar metallicities. So in these two panels, again, I show the O3 and H beta equivalent width as a function of the stellar age, but this time we consider the very low stellar metallicities. So with fixing the gas phase metallicity to 0.2 solar, we change the stellar metallicities from 0.2 solar to 0.006 solar. Yeah, and calculation results are shown in these different colors. So as you can see, if we consider very low stellar metallicities, for example, the stellar metallicity less than 1% solar, then we can reproduce the observed very high O3 equivalent width in these galaxies with a very young stellar age less than 3 megayear. Okay, so this indicates that we need a very low stellar metallicity to explain the observed very high O3 equivalent width. Okay. Another possibility to explain these kind of extreme emission lines are the non-thermal ionizing sources. So as I explained before, one of the galaxies, HD1, shows a helium-2 emission. Okay, and actually the helium-2 to H beta flux ratio is 0.03, so it's very high compared to the stellar population models. So this figure shows the helium-2 to H beta flux ratio as a function of the H beta equivalent width, and ID1 is located here. So here these lines are calculations based on the photoionization models with different stellar age, and also I show the predictions from high mass X-ray binaries. So as you can see, these models cannot explain the high helium-2 to H beta flux ratio. So this indicates that we need non-thermal ionizing sources to explain this high helium-2 fluxes, helium-2 flux, such as, for example, the metal poor AGN or ultra-luminous X-ray sources. So, for example, this figure shows the expected ionizing spectrum for ID1 constrained by the MC-MC fitting to the emission line fluxes. So this line is the expected ionizing spectrum, and this blue line is the classical stellar population model. So as you can see, we need more ionizing helium to ionizing photons than classical stellar population models. Okay. Also, we estimated ionizing photon production efficiency xi-ion. And actually, the estimated ionizing photon production efficiency is very high, 26.4 in log scale, both for ID1 and ID2. So in this figure, I show the ionizing photon production efficiency as a function of the UV magnitude. Okay, so our galaxies shows very high ionizing photon production efficiency compared to the previously studied high-redshift galaxies. And our ionizing photon production efficiency is comparable to this star mark, which is the extreme Lyman emitters found in the MUSE survey. So this indicates that the very high ionizing photon production efficiency in these galaxies and maybe in these extreme Lyman emitters are enhanced by the very metal poor stars or non-thermal ionizing sources. Okay, then here I will summarize my talks. So in this study, we studied two most extreme O3 emitters at a redshift of 0.8. The O3 equivalent width is about 5,000 to 6,000 angstrom, which is very high compared to the previously studied galaxies. Okay, and helium-2 is detected in one of the galaxies, and gas phase metallicity is constrained to about subsolar, constrained by the direct temperature method. Okay, so in order to explain this very high O3 equivalent width, we need very low stellar metallicities less than 1% solar or non-thermal ionizing sources. Okay. So this indicates that high equivalent width galaxies at the epoch of the reionization may also be powered by low stellar metallicities or non-thermal ionizing sources, which may be has confirmed by JWST observations in near future. Okay, so that's it. I'm happy to have questions.
Okay, thank you, Yuichi. Again, please enter questions in Slack in the Q&A. Yuichi has kindly posted all of his slides there already, or you may raise your hand. Yes, Michael Masada.
Hi, yeah, great talk. You explored the IMF variation in terms of the high mass slope, or sorry, the high mass cutoff. Did you look at different shapes of the IMF, for example, and see if that could also potentially reproduce the equivalent widths that you see?
Yeah, it's actually good question. Yeah, I think it's a good question. And currently, I only explain, I only consider salpita IMF with different mass cut. Yeah, it's good question, but yeah, it's good question. Yeah, I will how say, yeah, consider that later. So I think you mean the kind of very bottom heavy, no, top heavy IMF, right?
Yeah.
Yeah, okay. Yeah, it's good.
Okay, thanks.
Yeah.
So I'll ask a question related to that. I mean, I was wondering which stellar population models were used in the cloudy calculations, and whether you compared, single stars and binary star models.
Yeah.
And whether you explored the new Charlot and Bruce-Wall models.
Yeah, here I consider the BPAS model because the BPAS may have a more ionizing photons than kind of a single star population model. Yeah. So we consider the binary population model.
Any other questions? Okay, Jorit, Mattia, we have question from Slack here. Hi, Yuichi. Really interesting objects. I'm wondering about the stellar mass of these objects, which seems quite high given the equivalent width. Do you think the high equivalent width is effectively due to a new young starburst on top of an older, more massive component? Any evidence for that in the imaging?
Yeah, that's also a good point. Actually, in the images taken by the ground-based data, these galaxies are very compact. I can show the image. So yes, so these galaxies are very compact, And actually, ID2 is located in the cosmos field, and I also checked the Hubble images, but this ID2 is also a kind of a very compact. So I think that in that sense, the old stellar there are no kind of such evidence for old stellar populations.
Okay, thank you very much, Yuichi, for a wonderful talk.
Thank you.
And we will move on then. Kristan, if you could put your slides up. Our next speaker is Kristan Boyett from University of Melbourne, who will talk to us about the O3 equivalent width distribution at redshift 2, evolution of extreme emission line galaxy abundance.
Perfect.
Take it away, Kristan.
And can I just check that you can see my slides and hear me
We
properly?
can see your slides. It looks great.
Perfect, perfect. Okay, thank you to the organizers for allowing me to give this talk, which is, as you said, is all about the O3 equivalent width distribution at a redshift of 2. And this follows a recent submission that myself and my collaborators have made. And I encourage you, if you've not seen this yet, to go and give it a read afterwards. So in this paper and in this talk, I'm going to be considering why the objects with very large equivalent widths, those extreme emission line galaxies, are of interest. We've already heard so far today why, but I'm going to tell you a bit more. And I'm going to tell you how in our work we have investigated their abundance within the star-forming galaxy population at a redshift of 2, and then look at how that abundance changes with redshift as well. So to start, at high redshifts, above a redshift of say 6, during the epoch of reionization, numerous surveys have detected galaxies with extreme line emissions. One method has been to identify galaxies with an excess of emission between 2 Spitzer IRAC channels, where a flux excess can be attributed to the presence of emission lines with high equivalent widths, basically line contamination of a broadband filter. And this can be seen in the top right-hand plot here by Smith et al. 2015. Now, numerous studies have identified high redshift galaxies with large either H alpha or O3 plus H beta equivalent widths using this method, and many individual objects have been observed to have equivalent widths in excess of 1,000 to 2,000 angstroms in the rest frame. Now, these large equivalent widths can be linked to having a strong emission line flux relative to their stellar continuum, and this is indicative, as you said earlier, of young stellar populations. And this can tell us about star formation rates going up in a burst or simply an upturn in these high redshift galaxies. And these can also be linked to the formation of these bound or these dense star clusters. Now, further details of the ionizing conditions of high redshift galaxies that tie in with a picture of young stellar populations have been the detection of high ionization carbon emission lines such as C3 and C4. And Peter gave a talk yesterday all about these lines as well. And these tell us, or these indicate, that high ionization conditions exist in these high redshift galaxies, which are not typically seen in galaxies today. Now, at more moderate redshifts, studies have leveraged larger samples of data and spectroscopy to examine the relation between the equivalent width of these star-forming galaxies with their ionization conditions. For example, here's a plot from Tang et al. 2019, and they looked at a sample of redshift 2 objects, and they found a clear trend between the O3 5007 equivalent width and the ionization photon production efficiency. And here, these extreme objects, for example, above an equivalent width of, say, 750 angstroms, which are marked in yellow, clearly have an ionization efficiency elevated above the canonical values at this redshift. And the same study also found that the same high equivalent width objects also have elevated O3-O2 ratios, i.e. the O3 to indice, which relates to ionization parameter. And again, this is particularly important because other surveys and other studies, such as Nakajima et al. 2019 here, have shown that it's only the galaxies with large O3-2 indices that have the potential for large ionizing photon escape fractions. And again, I've tried to shade here in yellow roughly the region of the diagram where you're getting equivalent widths in excess of 750 angstroms, for example. So basically what we're saying here is that these studies at high redshift and moderate redshifts have revealed that EELGs have enhanced ionization characteristics compared to typical systems, and of interest especially during the epoch of reionization. And this brings us on to the work in this paper here, where we wish to understand the abundance of these most extreme objects, those with the largest equivalent widths within the star-forming galaxy population. And we look at a redshift of 2, because at a redshift of 2, the O3 emission line falls within the G141 HST GRISM. And here is a spectra from this GRISM slitless spectroscopy of a very strong O3 emitter. And we team this GRISM slitless spectroscopy from 3D HST with the multi-wavelength broadband photometry, also from 3D HST in the Goods North and South field, also the recent addition of a couple of UV filter coverage by the HDUV survey. And we do this to try and constrain the photometric redshifts. And we select a sample of about 700 objects with photometric redshifts in the range of 1.7 to 2.3. And again, we're looking to get that O3 emission line in the GRISM slit spectroscopy so we can measure its emission line flux. And we enforce an MUV cut down to -19. And this is to mimic the selection of objects at higher redshifts. And then what we do to work out the equivalent width of all of our objects, or at least the upper limit on the equivalent width, is to compare the emission line flux from the GRISM slitless spectroscopy to the stellar continuum flux density, which we get from the photometry. And then we use some Bayesian modeling to fit a best fit functional form to the equivalent width distribution. And that is shown here in this plot. And the point is that these EELGs, those galaxies with very high equivalent widths, which are ideal ionists, they have better ionizing characteristics than typical galaxies, are rare at a redshift of 2. And if you look at those with an equivalent width above, say, 750 angstroms, they account for less than 4% of star-forming galaxies at this epoch. So whilst these extreme objects may exhibit an elevated ionization photon output, the low abundance means they do not dominate the total ionizing emissivity of these star-forming galaxies at this redshift. Now, all of this stands in stark contrast to what has been seen at high redshift. For example, a study by Ensley et al., 2021, they found that these galaxies with these large equivalent widths are more common than what we found at a redshift of 2. So they had a Lyman alpha break selected galaxy sample using narrowband and broadband imaging, and they selected out 20 galaxies at this about a redshift of 7, and they used the IRAC-XS method to measure their O3 plus H beta equivalent widths. And like us, they measured the equivalent width distribution. And if I compare these together in this diagram here, you can clearly see that when plotted together, there's a change between these two equivalent width distributions. That at a redshift of 7 is clearly shifted towards higher equivalent widths than our work at a redshift of 2. And if we look at that plot again, but in this case, this time we look at what fraction of star-forming galaxies exhibit an equivalent width above a given threshold. For example, above 750 angstroms, that value we've been using throughout this talk, we can see what that fraction changes with redshift. And we see this factor of 10 increase between a redshift of 2 and a redshift of 7, going from roughly 4% up to about 40%. And we fit a power law to this as well. And what this really means is that a greater fraction of the star-forming galaxies during the epoch of reionization meet the conditions that we see at lower redshifts for the potential of large escape fractions of ionizing photons and having high ionization efficiencies. And in summary, I'll just repeat that these EELGs are galaxies that exhibit extreme equivalent widths and have been observed both locally and out into the epoch of reionization. their strong emission line flux relative to a stellar continuum is indicative of young stellar populations, which display higher ionizing conditions than typical galaxies, and they have a potential for these large escape fractions of ionizing photons. And we have determined in our study that while these efficient ionizing agents are rare at a redshift of 2, we find that their abundance increases with redshift by about a factor of 10 out to a redshift of 7, where these galaxies in this extreme phase will likely dominate the ionizing emissivity output of these star-forming galaxies at this epoch. And this is only a short 9.5-minute talk, so please, I'm happy to discuss more in the questions, and of course in a breakout room afterwards as well. Thank you.
Right, thank you, Kristan. Do we have any questions? You can enter them again in Slack, where the link to the AstroPH paper has been posted. Okay, Matt Malkin, please.
A beautiful use of Grisham's spectra, but you may, I guess, not be aware that there's a rather crucial data point at a redshift of 3 based on very strong excess in the K-band, broadband, photometry caused by extremely strong O3. And, there are 2 points. First of all, it's kind of remarkable that just from a redshift of 2 to 3, the oxygen 3 really seems to turn on, particularly in the low luminosity galaxies. And these were stacks, using 5,000 galaxies. So we're talking about the average oxygen 3 becoming very strong in the low luminosity or low mass galaxies. So I'm not sure how that fits in with you, but it seems highly relevant to include it.
Sounds very relevant. I mean, in our study, we have a relatively limited UV luminosity dynamic range. And so we weren't really able to examine any trend with UV luminosity in terms of which galaxies had these extreme equivalent widths. And so I think that can definitely be of further interest both to this study and, of course, future surveys with James Webb and Euclid and all those such other. But I'll happily read that paper if you can send me a link to it.
Sure, will do.
Thank you.
Thanks.
Matt, if you can put it in the Slack messages.
Oh, you're so nice. Okay, will do. All right,
okay.
Thanks.
So I have a question then, Kristan. I'm curious how complete you think the samples are at high redshift. I mean, we're seeing a population that's skewed toward these extreme emission line galaxies, but they're also the easiest ones to detect.
Yep, that is very true. But I think in the high redshift survey, which I compared to Ensley et al., do a good job in selecting the objects through a method, or at least a characteristic, which is not dependent, for example, on the emission line strength. So they're looking at the Lyman break again. So their objects in their sample cover a decent dynamic range in equivalent width as well. So they're not just selecting those with the highest equivalent widths. So although, of course, larger samples and more statistical significant samples are needed at high redshift, I don't believe that the trend we find is due purely to a bias, for example, in one of our samples.
Okay. We have another minute here if there's further questions. Kristan did a great job of sticking to time. I mean, I guess I'll ask one more question then, a similar one. When you're comparing the low redshift and the high redshift sample, are the stellar masses of the extreme emission line galaxies systematically higher for the higher redshift samples, just because you need more massive luminous things to detect them, or are they actually similar?
There's definitely papers out there and studies that have examined the trend between the O3 equivalent width with stellar mass. I know there's a paper by, I think, Reddy et al., maybe 2015 or 18, who study this. I think in terms of the two samples that we have here, the mass, stellar mass, which we get from, say, the photometric SED fitting, is roughly comparable, but that's not something either of our two papers looks into in particular focus.
Okay. Okay.
I'm also happy to answer questions further.
Okay, thank you, Kristan. There'll be another opportunity to follow up with more questions during the discussion later in the breakout rooms. Mattia, if you go ahead and put your slides up.
Yes.
Our next speaker will be Mattia Sirressi from Stockholm University. Mattia is going to talk to us about HARO 10, a local window on star formation in the young universe. Take it away, Mattia.
Exactly. Can you hear me well and see my slides?
We can see the slides and we can hear you.
Great. So, hi everyone. I'm a PhD student at Stockholm University under the supervision of Angela Damo and Matthew Hayes, who gave a talk earlier today. And I will present one of my first projects of my doctoral studies that I've been working on together with other collaborators listed here below. Let's start with an overview of this dwarf starburst galaxy named HARO 11. It has been detected at redshift 0.02, so relatively nearby. It is the closest confirmed Lyman continuum leaker, even though the percentage of photons of Lyman continuum photons escaping the galaxy is only 3%. It has a complex ionized gas morphology with bubbles, arcs, filaments, and channels that are produced likely by the central starburst, which is the feedback energy, the feedback engine of this galaxy. And it is the main focus of my work that I'm gonna present. I want to draw your attention in particular to three properties of this galaxy. The star formation rate, which is about 20 solar masses per year, the low metallicity, about 0.2 solar, and the Lyman alpha emission, which is quite strong with an equivalent width of 20 angstrom. In this image, you can see the three starburst knots of this galaxy. You see here knot A, knot B, and knot C, which we will refer to also later. And in blue, you see the Lyman alpha emission, mostly around knot C. So these three properties, together with the fact that the stellar luminosity is the typical of luminosity of galaxies at redshift 3, make this local dwarf similar to a class of high redshift galaxies known as Lyman break galaxies between redshift 3 and 5. The problem with this class of galaxies, even though they're very interesting, they're hard to study in details. But HARO 11, fortunately, is quite close, so we can have high resolution images. For example, like this one from Hubble. We see also plot marked with circles the clusters detected with photometry. These are the clusters older than 10 million years, and they appear mostly in knot A and in knot C. If we then look at the clusters with an age between 3 and 10 million years, we see that they appear not only in knot A and knot C, but also in knot B. And the youngest clusters with age lower than 3 million years appear mostly in knot B, and they're marked also with a red color indicating high reddening attenuation coefficients. So knot B is not only the youngest knot, but also the more dusty. And it's quite interesting to see over time the propagation of star formation from the eastern side of the galaxy towards the western side of the galaxy. In the second part of the project, we also studied the spectroscopy, because we wanted to have information not only on the clustered star formation, but also on the diffuse stars. So we combine far UV spectroscopy with COS together with optical spectroscopy from Muse. And we match the aperture for these two spectroscopies. And here I show the three circles that we use as an aperture. These are centered around the three knots, A, B, and C, and they are 1 kiloparsec diameter in physical size. Here I show the spectroscopy for knot A. On the left, the far UV portion, and on the right, the optical portion, which we model with Starburst 99 stellar libraries, and using a model made of multiple stellar populations. The orange population 1 is the youngest, and POP2 and POP3 are older populations. And I want to draw your attention to the P-Cygni lines, nitrogen 5 and carbon 4. These are the spectral features that are the most important for this fit, and in particular for constraining the ages of the stellar populations. And that's because these P-Cygni lines are produced by stellar winds in stars between 1 and 3 million years. So this modeling of the stellar population is important and useful, first of all, because we can derive the parameters of the stellar population, such as ages, metallicities, masses, and reddenings. But also, we can derive the feedback quantities. Feedback has always been quite challenging to constrain observationally. In this work, we measure three properties: the photoionization rate, the mechanical luminosity, so the mechanical power of stellar winds and supernova summed together, and their integrated mechanical energy. And we'll come back to these numbers later in the presentation. In the last part of this work, we studied the ionized gas, both the kinematics and other physical properties. Here I show some optical emission lines, oxygen 3, H beta, and sulfur 2. The first row is for knot A, and the second row is for knot B. These lines are well described by two Gaussians. One narrow component showed in green, and one blue component showed in blue, which is also blue shifted. And with the S sulfur 2 density diagnostic, we can measure the density of this gas, the mass, and the maximum velocity, about 400 kilometers per second. And assuming that this broad blue shifted component is tracing an outflow, a compact outflow, we can measure the outflow rates. So by comparing the properties of the ionized gas and the outflows, we, together with the feedback measured modeling the stellar population, we can trace back the history of these three knots of the HeII galaxy and the history of their outflows. So in knot A, we see the strongest outflow with a mass loss rate 10 times higher than the star formation rate in this region. Therefore, this knot is quenching itself. And here, the energy from the stellar feedback has been efficiently transferred to the bulk motion of the ionized gas. not B has a young dense outflow that is still in development. The mechanical power from stellar feedback in not B is quite large, so it is likely that this feedback will make the outflow grow and in energetics. And finally, in not C, we don't see any strong outflow. We speculate that this is a region evacuated by a previous outflow, which is consistent with the supernova feedback that we measure in this region. Over the past 40 million years, there has been the highest supernova feedback in not C. So one of the most important aspects of this work is the methodology. With our methodology, we were able to combine spectroscopy from different instruments. In a similar way, in the future, it will be possible to observe more distant galaxies and combine the rest frame optical spectroscopy from JWST with the rest frame fire-V spectroscopy from ELT. And ELT will offer the fire-V portion, the portion of the spectrum, so it will be very useful to constrain the ages, as I showed before, of ages of the stellar populations. And JWST will be crucial to infer the properties of the gas with optical emission lines. However, we will stay blind to the dusty regions of the galaxies. One point I would like to conclude with is that JWST will allow similar studies to the one I just presented on a large sample of high-redshift galaxies, and thus it will enable statistics, which is a fundamental tool for a more complete view on galaxy formation and evolution.
Great. Thank you, Mattia. So this paper is open for questions. Again, you can enter those in Slack or raise your hand. While we're waiting on the questions to come in, I'll ask one, Mattia. Yeah. I'm curious, you had the multiple Gaussian components that you fit to the optical line profiles in the MUSE data.
Yes.
I missed whether there was a one-to-one correspondence between any of those components and the three clusters A, B, and C.
So you mean if the velocities of this, for example, broad component matches the velocity in not A matches the one in not B?
Or more so, I was thinking spatially, if the broad component was associated with the whole complex, or whether it was localized at the position of A, B, or C, or maybe the spatial resolution doesn't let you address that, but I was just curious.
Yeah, it's something that we try to understand. In not A, not B, the kinematic is definitely similar. So we had basically the same thought as yours. That there might be like we might be tracing the same gas component on a large scale. However, in not C, we see different kinematics. We don't detect like this broad component is very faint in not C. So there definitely there is something different, and that's also the reason why I don't report here the optical emission lines in not C. So this difference between not A and not B and with not C favors for a more distinct gas components for each knot.
And I'm checking the Slack here. I'm not seeing questions there. Okay, we're almost out of time, but I'll take another minute to ask one more question if no one else is, because I find this work really exciting, Matthias. This is great.
Thanks.
I'm curious, you mentioned the nitrogen 5, the P Cygni lines from the winds was a strong age indicator. Yeah. And I'm wondering, I could imagine, I don't know if this is true, I could imagine that the absolute age you get is very sensitive to which stellar population synthesis models you use, but that for a given model, the relative ages were robust. I don't know if that's true. I'm just curious whether you've explored, I think you said you used Starburst 99, if you've made any comparisons to other population synthesis models and what effect that might have on the ages.
Yes, we are aware of of the presence of different models, but we have used only Starburst 99. We might explore in the future other models that take into account binaries, for example, BPAS, and that's something, yeah, very interesting to investigate.
Okay, thank you very much, Kristan. Or sorry, Mattia.
Thank you.
Again, you can ask further questions of Mattia in the breakout sessions after the next talk. If you could put your slides up. Our next speaker is Yi Xu from University of Tokyo.
Sure, thank you for introducing.
Yi is going to talk to us about outflows from low mass galaxies and their unexpectedly weak feedback, ?
Yes, so I think I will just start. And I really appreciate this opportunity to give this presentation. I'm Yi from University of Tokyo. And today I will share some results on the outflows in low mass galaxies with stellar mass 10 to the 4th to 10 to the 7th solar mass. And the interplay between star formation and the gas is quite interesting topic because the momentum and the energy input from massive stars and the supernova exposures can expel the surrounding gas and launch outflows. This procedure will also regulate the star formation, and it's known as the stellar feedback. In the low mass region, many theoretical and simulation studies suggest a strong energy-driven outflow. Using the indicator of mass loading factor, which is the outflow rate divided by star function rate, simulation has suggested a high mass loading factor as high as 100 in low mass region. However, the direct observational constraint is still missing. And in this study, we work on 21 local galaxies with stellar mass 10 to the 4th to 10 to the 7th. These galaxies are mostly selected from the Empress project. The others were taken from several studies that also investigate local low mass star-forming galaxies. And as you can see in the star formation rate stellar mass plot, these galaxies are undergoing active star formation, and the active star formation may power detectable outflows. To look for the signature of outflows, we try to resolve the HL alpha line profile with spectroscopy taken from Magellan Mage. The Mage spectral graph has a median high spectral resolution of 4,000. And another important thing is the sensitivity. For all our galaxies, we managed to get signal-to-noise ratio around 1,000 for H alpha lines. As an example shown here, our data have higher signal-to-noise ratio compared to Freeman et al. 2017, who successfully detect outflows. And we thus believe our data are sufficient for analyzing the line profile. Here I show one object where the spectra are shown in black lines and the blue line shows a single Gaussian, specific single Gaussian. In the zooming panel, we can clearly see the broad wings, and at the same time, the residuals are large, way larger than 3 sigma, implying complex structure that are different from the Gaussian.
So first, because the line signal to noise ratio is high, we need to consider other possibilities like the void profile comes from the natural broadening and the instrumental profile. Here we take the natural broadening parameter of this and fit the emission line with the void profile. And as you can see, there's still clear broad wings and the residuals are large. For the instrumental profile, we take the skyline, and similarly, there still exists broad wings and large residuals. So we are thinking the broad wings are mostly likely from a secondary component that matches the outflowing gas. So here, similar to many previous studies, we fit the emission line with double Gaussian, show us the red lines, and the red dashed line indicates each individual components. As you can see in the zooming panel, the broad wing are well explained and the residuals are also significantly reduced. So we apply the same fitting to the 21 Galaxy and find the double Gaussian profile while explain the shape for the 14 Galaxies. And here we are, we have the outflow detections. And the next step, first we calculate the flux ratio between broad and narrow components. Finding that with the high sensitivity data, we can cover a large range of this flux ratio, which may imply a variety in the outflowing mass. And we also calculate the maximum outflow velocity with this equation that accounts both the center wavelength and the line weight of broad components. Finally, we obtain outflow velocity of 50 to 200 km per second, and we investigate its scaling relation with the host galaxy property, that's stellar mass and the star function rates. So as you can see here, there's a trend for smaller outflow velocity towards smaller stellar masses, which may also exceed the fuller star function rate, but we also notice that there is a 1-dex difference compared to these massive galaxies with similar star function rates. We think the stellar mass is more important here. Another well-known scaling relation is with the circular velocity of diameter halo. For the massive galaxies, this relation is supported by observations and also simulations, while the low mass end is unexplored. Here we estimate the circular velocity from halo mass. We adopt the stellar mass halo mass relation for low mass galaxies. And here we are, our galaxies fall on this consistent relation between Vmax and the V circular. Knowing Vmax and the V circular, we can try to answer one important question about gas escaping. The gas escaping is directly linked to the chemical evolution of galaxy and the IgM-CGM. One scenario is that gas escaping is easier in low mass galaxies because the shallower gravitational potential well. And in our results shows that also with large error bars, the majority have no clear signature of gas escaping. However, we cannot rule out the possibility that a fraction of outflows can escape. And in particular, we found one object that has Vmax over V escape around 3. That makes it very interesting for further analysis. The last thing I would like to share is about feedback strength quantified by the mass loading factor eta, which is frequently used in observation studies and simulations, particularly in the PHI simulation run by Muratov et al. 2015. They develop a criteria at 60 km per second to classify the outflow into energy driven and momentum driven, where they expect this steep trend between eta and the circular velocity. In this study, we explore the galaxy fall into this region, and then we calculate the eta adopting the constant outflow velocity model, where the flux ratio and the Vmax are directly observable, and we need to estimate the properties
parameter that's electron density and the outflow extent. As a result, we obtain small eta values of 0.1 to 1, which is similar to or slightly smaller than those of massive galaxies. We are wondering whether these values are given by the uncertainties of electron density and R out. So we take extreme parameters that are 10 per cc and 20 parsec, which is quite low, and we still do not manage to produce high eta around the 100. So our conclusion is that in our galaxies, it's most likely that the eta value is small, indicating weak feedback. So here is a brief summary. We have detected outflows in these 14 local mass galaxies in a stellar mass regime that rarely explored by previous studies. And we calculate outflow velocity of 50 to 200 km per second with well scaling relations with host galaxies. We do not find clear evidence of escaping, and we think in these galaxies there are probably weaker feedback. So that's it from me, and now I'm open for any questions. Thank you very much.
Thank you, Yi. Again, you can ask questions on Slack in the Q&A, or feel free to raise your hand. We've got some time for questions here. While we're waiting on those questions to come in, maybe I'll ask one technical point, Yi. I'm curious, you showed the fits to the broad component with the Gaussian. And then I wondered how you went from the broad component to your estimate for the maximum outflow speed.
Well, okay, so I think I adopt this equation that accounts the line weights for the broad component.
Gotcha.
And
Okay.
also the shift of the broad component relative to the systemic velocity.
Thank you. I missed that. Other questions here?
Sorry, I have a question. Can you hear me?
Can you raise your hand?
Oh, sorry, I don't know how.
On Zoom, there's a little button at the bottom. I think under reactions, you can hit the raise hand, or you can type it into the Slack channel. In a pinch, you can put it in the chat. Alejandro, yes.
Sorry for that. Thank you. I missed the last question due to an error, so forgive me if this was the question already asked, but I wanted to ask, first of all, thank you for the talk. Very interesting objects and very interesting analysis. I was wondering about the secondary peaks that you see here, the smaller residues there that you were mentioning that could be indicator of actually more and other components. And did you analyze those? Because I remember a paper from the group of Sanchez Almeida as well, that they analyze the H-alpha line profiles of this kind of galaxies, and they found some interesting results with the, I think what you call there the small residuals. So thank you. I can type the paper in the Slack so you can have a look at it if you haven't.
Well,
thank you.
Thank you very much for sharing this information. I would be very interested in that paper. It would be great if you can share it in the Slack.
Sure, I'll write it down.
That's great feedback. Thank you.
Yes, thank you very much.
Let's move on then. Shenfeng Xu has a question.
Hey, very nice talk. So I don't know if I missed it. So one of the questions is for these galaxies, have you used a statistical test to see if they really need a second Gaussian? For example, you can use the F-test to see. I doubt some of these galaxies have very small velocity and small feedback. Maybe they just do not need a second Gaussian. So maybe you need to statistically test them there.
Yeah, that is a very good question. And yeah, we try to establish the statistic method, like using reduced chi-squared. And Yeah, it turns out that our Galaxy sample is not very large, and we found it would be great to just check this residual plot individually. And
yeah, you can use the F-test to basically compare the single Gaussian fit to a double Gaussian fit, then to see if statistically it is acceptable to have a second Gaussian. Because sometimes the single Gaussian didn't fit well just because the Gaussian is not good for this object. Right. So yeah, it's difficult to accept it by eye. So you can just try to see, use some F-test to basically better quantify it. Okay.
Thank you for the feedback.
Thank you.
Okay, any further questions? I'm not seeing the reference to the paper appear on Slack, Alejandro.
I'm coming, sorry.
Okay, it's coming, okay. Just worried it ended up in the wrong place, great. Well, I wanna give a big thank you to the speakers from session 1D here, and to those of you who asked questions. This was great discussion, which we now have an opportunity to continue in the breakout rooms. I also want to draw attention to the poster room. In the breakout rooms, if you click on breakout rooms in Zoom, you'll find the rooms listed, and it includes some posters you can see listed under breakout rooms, and I encourage you to go talk to the people with posters. And there'll be an announcement in about 20 minutes that our session is officially over, but you are free to continue discussion at that point in the breakout rooms if you're in the middle of something. So thank you very much. And we'll see you in the breakout rooms. Yuki, are you still online?
Yes.
So I'm looking at the breakout rooms. How do I get the little join button to come up? I'm somehow doing this wrong. If I want to move myself to a breakout room.
Oh, can't you go to the any breakout room? No?
Just put mouse on the number of the people and it will appear join.
Oh, on the number. That's my problem. I keep putting it on the name and the arrow.
Is it working?
Got it.
No problem.